My name is Jérôme Pilliet. I'm the PhD student of Rémi Forax. And I work on the implementation of the JSR 292 on Android. Why we do that? Currently, a dynamic language runtime developer have to see Android like an environment with a specific JVM. And some languages, like Groovy, run only on the JVM. And obviously, Android developer are Java developer, and they can't use Java features. So, unfortunately, I can't show you the demo in the real device because I can't connect the device. So I will show you the demo on the emulator. So it's our Android with our modification. Hop. Where I am. Okay.
Just it works.
Okay. Just not connect the projector. We have an application. Okay. In this application, we have three ways to invoke a method. We use the reflection, a call of InvokeDynamic, and a call of Invoke Exact. So we execute, we invoke 1 million times the method, and we calculate the execution time. Okay. So in the emulator is a little bit long. Yes. It's a problem, but it's the emulator. So the reflection is already on Android. It's not works. So okay, it's finished. It takes 27 seconds to execute 1 million times the method. If you test InvokeDynamic, it's more quickly. Tuk, tuk, tuk. Okay. It takes 6 seconds, 7 seconds. And with Invoke Exact, okay, 6 seconds. The difference between Invoke Exact and InvokeDynamic is InvokeDynamic have a volatile read, so it takes a little bit more time. Okay. Tick, tick, tick. But up.
Is this one? No.
No. We have lost the talk.
Oh.
Okay. Okay. We don't see the same thing. Okay. So the problem is Dalvik, the virtual machine of Android, is not a real Java virtual machine. So we have to adapt the JSR before implement it. Some difference. Dalvik is a register-based machine, and Android run on constraint environment. So we have to save the memory and the battery.
And because we do this after the spec, we have cleaned some part of the spec. Oh.
Okay. Dalvik can't execute directly Java bytecode, so it translated on a Dalvik bytecode called DEX for Dalvik executable, and it can optimize this bytecode with the tool DEXopt. This optimization is when the application is installed on the device. It's a static, it's an offline optimization. The DEX file contains the bytecode, is read-only, contains several classes, and have one constant pool by type. The idea is to have a short instruction with a short index. So, Dalvik virtual machine, DVM, is a register-based machine, have several interpreters. We work on the portable interpreter because is wrote all in C. It's more easy to develop. The JDK is wrote from scratch, and Dalvik have a non-generational garbage collector and a small JIT. So we had a new DEX format with a new header. Contains the 4 new constant pool. Constant pool for method type, MethodHandle, InvokeDynamic, and bootstrap method argument. And we add 5 new instructions. We have an instruction for Invoke Exact and InvokeGeneric. We call it InvokeGeneric because Invoke is already exists in the VM. So we use unused opcode, and each instruction has 2 formats. Depends of the number of arguments. If you have less than 5 arguments or more. In an Invoke Exact and an InvokeGeneric have an index of the method type constant pool, and InvokeDynamic have an index and InvokeDynamic constant pool, and the number of call sites on the table of call site, which is in the declaring class. Okay. The method types are intern in Java, and are opaque pointers on the VM because we have just to check if a match. Mm-hmm. For Invoke Exact and InvokeGeneric, we can resolve the method type and store it on the particular table. But we don't have to do for an InvokeDynamic because it's called just once. We have 3 rings of MethodHandle. We have the content MethodHandle. We are which are file accessor and method invocation. We have MethodHandle for lambda, bind constant, and we are combiners. In the VM, MethodHandle have a kind, so a kind for file accessor invocation, method invocation, bind constant, and we have two kind for call a specific interpreter to interpret a MethodHandle tree. We see that with Rémi after. A MethodHandle have a slot, a pre-calculated slot. Directly, it's an index to a table for a field, vtable, itable, etc. You have a declaring class and a method type. We have a hierarchy of MethodHandle. Some MethodHandle extend to MethodHandle and have extra field. We have the combiners, and we have two specific MethodHandle, which have a specific implementation on the interpreter. It's a constant MethodHandle and bool MethodHandle. So this is the schema of our macro in the interpreter. So when we have an Invoke Exact or an InvokeDynamic, we have to treat our argument. And for example, for Invoke Exact, we have to check the method type, and for InvokeDynamic, we have to get the call site and resolve it if we are. And we call a specific macro invoke row MethodHandle, which execute the MethodHandle, call the invoke method, real macro, an already exists macro on the VM, and or access directly on the field. For InvokeGeneric, it's a little bit more difficult, because if the method type doesn't match, we have to convert the argument. So we have a specific function. We use the reflection mechanism, and we access directly on the field, or we have to create a stack frame and call manually a method, because the dex file is read-only, so we can't rewrite it. Okay, it's a detail of the implementation of Invoke Exact. So the first argument is the MethodHandle. At first, we have to get the MethodHandle, and we have to rebuild the argument, because we want to reuse the invoke method mechanism of the interpreter. So we have to shift the argument. After that, we get the method type, and we check if a match. And if false, we throw a wrong method type exception. Else, we call the other macro, which execute the MethodHandle. For InvokeGeneric, it's almost the same of Invoke Exact. Just if the method type doesn't match, we don't throw a wrong method type exception. We have to convert the argument, boxing, and create a stack frame and call manually the method. And for InvokeDynamic, we have to get the current class, the call site index, and we try to get the call site if it's already resolved. If not, we resolve it when we get the indie reference on the constant pool of InvokeDynamic, and we have to do a Java call to call the bootstrap method, which return a call site. This method call an Invoke Exact on the bootstrap method. And after that, we enter the call site, and we call with the target. It's the volatile read, so we change the spec because it's more simpler to implement. If we have only a volatile read and not unsynchronize with the method. And we have to modify the garbage collector because some of code use Java references. We have a call site and method type used by InvokeDynamic, Invoke Exact, and InvokeGeneric. So the method types are intern and stored in Java, but just for Invoke Exact and InvokeGeneric. And call sites are stored in a class object on the VM and are routes for the GC. And now it's a Rémi turn.
So if we want to run a real dynamic language, we have to implement call to combiners like filter argument or guard with test and things like that. The main issue is we can't generate code because a grad student tried to do that. And if you generate code, I think it was with a Nexus 7, the battery lasts 20 minutes. So we can't really generate code. We can't really call methods. I mean, having a method handle that call another method handle that call another method handle, because each method handle is a really small brick of something like reorganizing arguments or things like that. And so we will end up with a lot of a really big stack trace where the interpreter spend more time trying to push and pop stack frame instead of doing real work. So why an unicorn is just we think that we will implement this in that way. So the main issue is combiners. And combiners are the base of basically, if you want to implement an inlining cache, you will use JWT and a lot of conversions. So first we will implement what we call the EST interpreter, which is basically just for each method handle, there is a specific method that will be called, and really like we will go from the C interpreter to a Java interpreter. Why doing this? We know that it will be slow, but we want first conformance with a spec, and having an implementation that we will able to diff with another implementation, which is the C implementation. So just let's take an example. It's really a small example. Let's say I want to implement this using MethodHandles. So I have if-else things in JSR 292 Sabir. It's guard with test, and you specify 3 MethodHandles. The first one is the test, which here what is done is to use bind to bind a specific instance of a random object, and next to call next boolean on it, which means that the random object is a real true constant here. And to specify 2 MethodHandles, the target that will be called if the result of a call here is true, or the fallback if the result is false. And here we have the part which show how to deal with conversion between, by example, a double to an int. This is done by using a combiner named filter arguments that is able to take a value, call a method that will do the conversion. So basically, we have a MethodHandle tree, and if you take a look to this tree, we mostly do 2 kinds of operation. Or we push value as argument, we swap arguments, or we go outside to call a Java method. So basically, if we want performance, the idea is to try to do all the swapping of arguments and so on in one stack frame, and to just create stack frame for call. So instead of having one stack frame, one call by MethodHandle, as you can see with the current implementation in a hotspot, where you have a lot of Lambda forms. We want to try to have one stack frame for all argument shifting and things like that, and one stack frame for each call. So the EST interpreter is really, really basic. In the class MethodHandle, we have a hidden method which is called InvokeEST, and basically we box all arguments and we will unbox the result value. So just to take an example, here's a GWT MethodHandle. We have the 3 MethodHandles, and InvokeEST is just calling the test method. We know that it's a boolean. If it's true, calling the target method or the fallback method. So this implementation is not, the idea is not to be efficient, but just to have something that works. And if, by example, in the example, we call random dot next boolean. So at the end, we will call an InvokeEST on a specific MethodHandle, and we have a big switch for all arities possible. hopefully in Java there is only 250 possible arguments. And we rely on Invoke, which is implemented in C in the interpreter. So after that, what we want is try to have a kind of mini interpreter inside the Android interpreter. We don't want to push stack frame for each method handle. So the idea is to try to resolve the tree of method handle inside one stack frame. So this stack frame is a little weird. It's not a classical stack frame, because when you call a method, the stack frame is defined by the argument that you use, and here you have to know the argument that the whole method tree will need to have. And because we have a mini interpreter, it means that we also have opcodes, special opcodes that we can run. And if we end up to generate this opcode, if we generate we generate one sequence of opcode for one method handle tree, it will be awful. It will be exactly like generating bytecode. I mean, it will have exactly the same issue. So for avoiding that, instead of manipulating arguments, instead of manipulating value, we will use index indirection, which means that all operation in the all opcode will manipulate only index. And when we will want to call a method, we will use index to find the real argument and materialize them in the stack frame and call the Java method. Because we think we will use index, we will be able to share the code between method handle tree. Basically, two method handle tree, if they are exactly are the same, we don't care about the method handles that are called. There are parameters. The only things that makes the opcode different are the type of method handle which is used, and the argument, and some argument, like by example, if you have insert argument, which is a method handle combiner, the position where you insert makes the bytecode specific, makes the code specific. So the idea is really to have an interpreter inside the interpreter. Whoa. So here is a tree of, I will not explain the whole thing. Do you want me to show how it works? But it's enough to say that we have a tree of method handles. We know the whole tree when we will create the stack frame. So we can calculate all the method handle we need. We need method handle because we will want to access or to their argument. By example, the constant here are stored in a method handle, or because we want to call it by example, the float to int method here. So for a MethodHandle tree, we can generate one code, and because this code use index and not value, I mean, the execution of this code works on index and not on value, we are able to share it between several MethodHandle trees. So for the specific stack frame, we have different things. We have the value, exactly, which will be different for each invocation. And we have here the index. So we don't show the encoding of the index because it's a little bit tricky, but basically this means this is a return value, which is a 32 bits value, or this is a bound data, which is the bound data of the second MethodHandle, which is here. So we have a specific encoding for that. So here is the code generated corresponding to this MethodHandle. I don't know how many people knows Android opcode, but as you can see, it's mostly exactly the same opcodes that the one that are used by Android. So we can use a trick, which is to reuse exactly the Android interpreter to interpret this sequence of opcode. Basically, what we want, this works by moving register, and Android is a register-based interpreter. So we can reuse it. We have only one method, which is the invoke frame image, which is specific to our implementation, which is the method that rematerialize the value to recreate a real stack frame. So this is the way you can see the stack frame and what is the encoding which is used. So what we think is that because we can reuse exactly the same interpreter, because we can reuse all the opcode that already exist, we just have to implement it one opcode, the invoke frame MethodHandle. We think that we will be able to execute MethodHandle tree efficiently, at least as efficiently as possible. So this is where we are and when we want to be. The Android SDK compiled with Java 7. We still have a pending bug in Java C7. Maurizio?
And Javadoc too.
We have modified all the tools to understand the new class format. We have not. There is something that should be done here, which is currently we have no transformation from the old format to the new one. I mean, from the format every Android device is used, but the one on the left here. But it's just in. We can do that when you install the application. When you install your application, we can change the DEX format to the new format. So it's not a big deal. And we have not finished the implementation of InvokeGeneric, but Invoke Exact and InvokeDynamic already works. So we will have to implement, or exactly, I just think he will implement the combiner, the EST, the mini interpreter, and we hope to have a Lambda, Java 8 Lambda an interpreter which is able to execute Java 8 Lambda really well, because basically the kind of method handle that are used are very specific. So we can implement really small methods, in fact 3 small methods, to be able to have lambdas that work on Android. Do you have any questions?